We are going to talk about memory hierarchy. Okay, in memory hierarchy, I also gave you some chapters or subsections of a chapter number 5 to read. I specifically gave it that number from the edition which I have supplied to you. The books have gone through several editions, and they do make radical changes. So, what was previously in 5.2 is now in 5.3, and so on and so forth. So I checked the textbook and then gave you the suggestion accordingly. Now, memory hierarchy is one of the most important topics that we will be studying here, because when you write a program, your program has to take into account the capability of memory. So, for example, if you write a great game, but if you go to your boss saying that this game would work well if someone has got 16 GB of RAM or more, then your boss will not be very pleased, for the simple reason that he would tell you that okay, 16 GB is not the norm. Try to make it run on 4 GB, because that's the lowest possible things available in laptop nowadays, and you want to increase your client base. You don't want to shrink it, that this game is useful only to those people who have got 16 GB of RAM in their laptop. So how to run your program efficiently without seeing glitches or taking inordinately long time requires a lot of idea about how memory works. And once you know how memory works, you then can decide how to write your program so that there are not too many memory misses, or too many under hits or something. I will explain what those words mean. So let us start in a very simple way. So we are going to talk about importance of fast memory access. Let's say you have purchased a processor which has got 1 gigahertz. This processor might be in your laptop or it might be in your phone. Now 1 gigahertz is slightly dated, but I like to give example of 1 gigahertz because its counterpart, that is 1 over frequency, that is equal to 1 nanosecond. So it's a very nice one-to-one correspondence. By the way, 2 gigahertz would make it 0.5 nanoseconds, and so on. 3 gigahertz would make the time period as 0.33 nanoseconds. So 1 gigahertz processor, you have got 1 nanosecond. So now what does that mean? That each stage which you have designed, say 5-stage pipeline, so fetch, decode, execute, data memory access, and write back, each stage has got exactly 1 nanosecond. And they have to finish their work in 1 nanosecond. So for example, the execute stage has to finish execution in 1 nanosecond. Your data memory access has to access data memory, bring back the data, or store the data in exactly 1 nanosecond. Same thing with fetch. It has to go to instruction memory and fetch the required address from instruction memory in 1 nanosecond. So now this sounds theoretically okay, but getting this and this in 1 nanosecond is not very easy. So what you are saying is that fetch, that is access to instruction memory and access to data memory, should be at the speed of the processor. So that memory speed has to match the speed of the processor. Not very easy. So what do we have to do? We have to decide on something. And let me give you an idea in very simple language. So the example is given is like this. So you are preparing for exams, and let us say you are on campus. So, and you have got exams of 2 subjects or 1 subject, and you have certain number of books on your desk. Now the books on your desk would be the ones which you need very frequently for that course. You will not keep extraneous book. You will not keep books which you might need after 2 days or 3 days. I mean, that will just make it a clutter. So you will just keep 2 or 3 books. Suppose there is some section in a particular book, which doesn't make sense to you, and you feel, you need to refer to some other book which is not on your desk. Then probably you will have to go to your cupboard. Your cupboard may have, say, 100 books, or your bookcase may have 100 books. So, you will look through those 100 books, and, suppose if it is there, you will take that book out and, bring it to your desk, and then again start reading. Suppose that book is not in your bookshelf either. Then you will have to go to the library. Now, library have got tens of thousands of books. And then you will have to search through the stacks, and it will take time, but it is definitely, you are going to find it over there. So the idea is that for computer or for a processor, this is your processor, and we'll call it as P. Now, processor demands memory access within 1 nanosecond. Suppose this is working at 1 gigahertz. So it demands that it gets instruction and data within 1 nanosecond. Okay, that's fair. How can we achieve this? The second thing which we discussed when we discussed about structural hazard was that we need to separate out instruction memory and data memory, because as we saw in the earlier slide, instruction memory is fetched in the first stage, data memory is shared in the 4th stage. So, when the pipeline is filled, while one instruction is trying to fetch something from data memory, another instruction, which is like, maybe 3 instructions down from here, would try to fetch something from fetch an instruction. So you can't have a common memory which stores both data and instruction. So what you are trying to do is separate them out. So that is what we have done, and that is most of the processors do nowadays. So now what you have is you have got access to your instruction memory and access to your data memory. Now, you have made a condition that, I want to get the data. So first, processor, when it sends a request that, this is the address in the program counter, I want to go to that particular memory location in instruction memory, get that thing and come back. So that means you don't have much time to look around, right? It's like, the difference between looking around in your bookshelf or looking around on your desk and looking around in the library. In your desk, if I ask you, do you have a particular book on your desk or not? All you have to do is take a glance, and you will figure out whether that book is there or not. If it is there, you can instantly give it to me. Otherwise, you will say, sorry, I don't have it. And then, of course, you will have to get up and then go to bookshelf. And then if it is not there, then you may have to go to library. But the advantage is that, having small number of books right close to me is a good idea, because, then retrieval is very fast. So that's why I have a small instruction memory and small data memory very close to my processor. And in the parlance of computer science, we call it cache memory. Please do not pronounce this as cache. This is known as cache, and cache means storage. If you read Times of India or any of the English newspaper, they would say that the cache of arms was seized from the terrorists. So basically cache means storage. So it is pronounced as cash, and because it sounds like cash, that means money, sometimes the symbol given to it is dollar, right? Because it sounds like cash. So we will, in example, you will see symbol like this, I and then dollar. So what I'm trying to say is instruction cache, and this is data cache. So what this means is I've got two small but very fast memory very close to the processor. And so that processor, if it asks for something, and whatever it wants, if it is found in instruction cache or data cache, it is done at the speed of the processor. So your processor can run fast. What that means is your instruction cache and data cache should have as much data as possible, right? Then you can say whatever processor wants can get it from there. But here lies in the problem. If I try to make my instruction cache and data cache too big, the advantage of quick search is gone. If I put 100 books on your desk and then say, okay, whether you have a particular book on your desk or not, then you will have to search through it. You will have to glance, look up, look down, and then you will tell me after maybe 10-15 seconds that no, you don't have that book. As opposed to if you had only 3-4 books, all you need to do is, it may take you a second, just glance and say, okay, I have it or I don't have it. So you have to make a compromise and make instruction cache and data caches smaller. The advantage you will get is that search is very easy. Immediately you will find out processor has asked for a particular address. If it is there, instantly you can pick up and give it to processor that here's your instruction or here's your data. But the flip side is that because it's a very small space and your program might be like 10,000 lines long, and this may be able to store say 100 lines of your program or 100 lines of data, and that is nothing as compared to the total size of your program. So then you have to have another backup, and you have to have slightly bigger memory, right? You call this as main memory, or in local parlance you call this as RAM, random access memory. Okay, so if you can't find something here or something here, then you have to go to main memory. Now main memory, as opposed to instruction cache and data cache, it's a unified memory. That means it can have both instruction and data. Only at the very last stage you separate them out, because then it makes sense. Providing large separate memory for instruction main memory and data main memory is too expensive. And electronics is now working on margins that you can't put unnecessary stuff unless you are an Apple owner who are ready to pay anything. Other than that, people are very cost conscious. So you have unified RAM, and which is over here, which is much larger. So RAM might be say 4 to 32 GB, and this might be 1K to 4K, right? Very, very small. So access time for this, if you find a data in instruction cache or data cache, it would be like 1 cycle. So 1 cycle could be 1 nanosecond for 1 gigahertz machine, or could be 0.5 nanosecond for 2 gigahertz machine, or 0.33 nanoseconds for 3 gigahertz machine. But anyway, the time is called a cycle. So cycle could be of any time limit, could be of 1 nanosecond, 0.5 nanosecond, 0.33 nanosecond. So here, let us keep unit as 1 cycle so that you don't have to worry about nanoseconds or anything. So if the time to get something, a data or instruction from here or data from here is one cycle, which is good, right? One cycle, one work done in your processor pipeline. But if you not find here and if you have to come all the way here, then it would take about approximately 100 cycles. Now, you were worried about, wasting one cycle in a bubble when there was kind of a bump because of raw hazard, and you had to put a bubble between, say, a load instruction and a dependent arithmetic instruction, and you are worried that, oh, this is one cycle is wasted. Here you would immediately waste 100 cycles. And what would happen? Suppose if this was rendering an image, and getting a pixel or forming a pixel is taking 100 times more, and then your graphics would be all pixelated, and nobody would want to play that game, or nobody would want to listen to music, or nobody would want to watch the movie, because then audio is all garbled or the video is all garbled, it is all pixelated. But that is the price you have to pay. So this is your main memory. Now, some people may say, oh, there's a huge gap. Yeah, this is one cycle and this is 100 cycle. Can't you put something in between so that, maybe a memory whose size is slightly greater than this, but less than this, and, access time is also less. So then, that is known as cache, but second level cache. So now, we change the nomenclature. So we call this as level 1 cache or L1 cache. And then, we put a slightly bigger cache, and we call it as L2 cache. And this is main memory. And the time difference, if it is not found, and again, this is also unified. This is not separate out in instruction and data. So that means to access this, you will have to waste 10 cycles. Now it is not as good as, getting a data or instruction in one cycle, but, it is much better than, getting a data or instruction in 100 cycles. So, so if this is 1K and 4K, then, this size of this would be 1 MB. Right? So L2 cache size would be 1 MB. And this is not just thing, this is very practical. See, till now, when you purchase the laptop, I'm sure you must have looked at the processor, whether you want to buy an i3 laptop, i5 laptop, or laptop containing i7 processor. You may have worried about RAM, that should my RAM be like 8 GB or 16 GB. Or, you may have worried about what should be your disk size, should it be 1 TB, 2 TB, should it be SSD, or should it be just, normal tape drive? So these were the things you were wondering. But, now as we go deeper into this, you will realize that performance actually comes from cache size. And, you may never have worried about what is the cache size. So now when you look at the processor details, try to look at the cache size. Now some of the people have started giving out cache size as one of the things in the normal advertisement, that, it has got L1 cache of 4K or 8K or 16K. So, you will see that, these small, very minute memory has got a lot of importance in improving the performance of your program as compared to your RAM. Of course, RAM is important, but this is much more important and, much more expensive than this RAM that you have. Okay. So now this is a very general thing, and, I have given you, and, we will be going deeper and deeper into this particular thing. But, as an introductory thing, you can understand why we have something called as memory hierarchy. And this is memory hierarchy. This is the smallest memory. So smallest and fastest. This is medium, and this is largest and slowest. Okay. So as you see that in one matrix, you go up. That means, oh, this memory is very fast. I love it. But then on the other hand, there is a downside that, it is very fast, but, it is slow. I'm sorry, it is very fast, but it is very small. And the second memory, it says, it is very large, but, it is very slow. So that's why, you have to make a judicious memory hierarchy. So that, okay, I will keep very fast memory, very close to my processor. And this design, as you will see in examples, which we'll do later in this particular topic, you will find that, the chances that you will find what you are looking for in instruction cache and data cache is close to 90%. And who makes sure that, it is 90%? That is going to be your operating system. That, that's why operating systems are so difficult and so important in running a processor, because operating system is like overall manager of the whole system. So operating system will make sure that 90% of the time you will find your instruction or your data in L1 cache. If not, you will have to go to L2. And if don't find it in L2, then, in some processors, modern processors now have L3 also. But, now let us assume that our processor, which we are talking about, has only two levels, L1 and L2 cache. So this is L1 cache, which is separated out, instruction cache, data cache. This is L2 cache. And then, we have one unified RAM. So that is more or less what we have. Just one second, the instruction cache and data cache. One second, let me read that question. Is the instruction cache and data cache separated physically? Yes, they are separated physically. So there are two different memories. Both of them have separate lines coming, so that this is 32 lines are here if it's a 32-bit processor to bring in instruction, and this has got 32-bit lines coming from here to get data, because both of them have to be accessed simultaneously. So both of them are physically separate for the L1 cache. For L2 cache, it's a unified cache. Then the reason you may ask that would it not make difference to have a separate L2 cache also? Well, yes and no. Yes means yes, it would make a difference, but no means it would increase the cost. You don't want to increase the cost. So L2, let it be unified. You don't want to give. Otherwise, the routing would be such a huge problem that every time you have got separate 32-bit lines coming. So L2 cache onwards. So L2 cache, L3 cache, main memory, they're all unified caches. So it contains both data and instruction. Okay. So now let us move forward. So I hope everything is clear up to this point. Now we'll talk about this. Now your L1 cache, you don't know why there is a difference in speed between L1 cache, L2 cache, and L3 cache. Now, of course, you say that this is smaller, so to searching through this is easier. This is larger, slightly larger L2 cache. So searching will take slightly more time, and then this is way too big, so searching will take more time. But also, apart from that, there's also a difference in technology. So this is something which is known as SRAM. I'm going to talk about this at the end of this thing, about SRAM, DRAM, flash, and hard drive, explain the technologies behind this. But right now, just understand that static random access memory, for which L1, L2, and L3 caches are made. And this static random access memory is made using state-of-the-art machine, and it requires 4 to 6 transistors to create one cell or to store one bit. And access time, as you can see, is in fact now it is even lower than 0.5 nanosecond. But let us assume it is 0.5 nanosecond to 2.5 nanosecond. So so basically what it means is L1 is running at the speed of processor. But look at the price per GB. It's very expensive. That price per GB, 1 GB of SRAM would cost you $500 to $1,000. So it is a lot of expensive stuff. So that's why you have just a bit of SRAM in L1 and L2 and L3. Whereas DRAM, what is conventionally called as RAM, but ideally you should call it DRAM, that is dynamic random access memory. So as the name suggests, dynamic random access memory means, the word dynamic means that usually it is like a capacitor. If you want to store one in it, in that particular DRAM cell, it's a capacitor, so you charge it. But what's the problem with a capacitor? It discharges, right? So there is a graph that it's slowly the charge goes out. So then you have to periodically refresh it. Otherwise it would lose. Whereas static RAM, as the name suggests, would keep whatever is in there. You don't have to refresh it. So in dynamic RAM, well, it's a very small thing. If you want to understand theoretically, it is just a capacitor that you charge it if it is 1 and discharge. I mean, keep no charge if it is 0. And then but then the problem with storing charge 1 is that it slowly discharges. So unintentionally, your 1 will be converted to 0 over a long period of time if you don't do anything. So that's why it has to be refreshed. So again, it has to be recharged, and again, it has to be recharged. So that is the word dynamic comes into it, and that is your RAM, what you call it as RAM. And you buy, say, 4 GB or 8 GB or 16 GB. That access time is 50 to 70 nanoseconds. So it's a sizable time, but the price per GB is not too much. It has come down drastically. Then there is flash memory. And this is also what you call it SSD drive. Right? So SSD drives are much faster than your hard drive. And again, it is a static thing. So flash memory is chosen. And then finally, there's your hard drive. If you're using an old style thing, where there's a header and then there's a tape which is moving around, then, that is quite cheap. You can get 1 terabyte of it for like what, 3,000 rupees or something. You can get it even cheaper. So hard drive is very cheap, but look at the access time, 5 milliseconds. 5 milliseconds is a lot of time. If your processor is doing 1 billion tasks in 1 second, and if you ask it to wait for 5 milliseconds, then it would say that in 5 milliseconds, I may use millions of cycles worth of work. So hard drive is the slowest, but it is also the cheapest. So this is a price comparison. Now, this is which we have already talked about. So what this particular slide is trying to tell you is that we need to achieve a right balance between performance and price. So you want good performance, you want your hit rate to be very high. When I say hit rate to be very high means you want to access your instruction memory and your data memory in close to 1 nanosecond for a 1 gigahertz processor. Then only you can say my processor is running at 1 gigahertz. But unfortunately, even if there's a 90% hit rate, and just 10% of the time you have to go to, let's just say, just to give you an idea that how important this is in determining your access time or CPI. Let's say you're using 1 gigahertz processor. So that means your access time is just 1 nanosecond. Now, I'm saying I got 90% of the chances, both for instruction and data. So let's just say right now I'm considering only instructions, okay? I'm not worried about data right now. I got 90% chances of what I'm trying to look for, I will find here. So you'll be very happy. But that also means that 10% of the time I'll have to go here, right, to the second level. And it is taking 10 nanoseconds, 10 cycles. That means 10 nanoseconds. Forget about this main memory. We are just talking about 2 levels. So then, someone would ask me, then what would be your average CPI of your processor? If you remember right from the first lecture, I was telling you that ideal CPI of an inline processor is 1. So that means everything is done in 1 cycle. Then, so once this thing, your throughput would be 1 instruction execution completed in 1 cycle, right? That is your throughput. But I also said that the slowest of these, slowest of any of these blocks would determine your throughput. So slower it is. So suppose if data memory access takes long time, then this would determine the throughput. So every block is taking 1 nanosecond, but suddenly this starts taking 2 nanoseconds, then your throughput would be after every 2 nanoseconds. So that means your CPI has effectively become 0.5. That means only you require 2 cycles to do 1 instruction. So your cycles per instruction would be, how much would it be? 2 cycles per instruction. So your CPI has become 2. And that is the problem. So now what would happen here in this particular case? So in this particular case, 90% is the hit rate. So if you want to find out average, so you will say that while calculation 0.9, that is fraction, right? 90% fraction after 1 is 0.9. So 0.9 times 1. So time taken here is 1 nanosecond. But there's a 10% fraction. So that is 0.1, which is taking 10 nanoseconds. So what is this? This is called average time for memory access. Right? We are going to study this in much more detail, but I'm giving you a very simple idea. So that, then, you will say, okay, my probability says that, 0.9 times, that means 90% of the times, I will get it in 1 nanosecond. But, there is a 10% probability. That means fraction 0.1, that, I will take 10 cycles. So this is average memory access time. It is known as AMAT, average memory access time. It becomes 0.9 into 1 is 0.9. Plus 1, right? So your total number of cycles taken would be 1.9. So now you start realizing that, this fetch cycle on an average would take 1.9 cycles on an average. So that means suddenly your 1 gigahertz processor has become 500 megahertz processor, right? Half the speed. So now imagine you are worried about losing 1 cycle for that raw hazard, or even 3 cycles when there was a branch and you said that, oh, I have to throw away whatever was here, and here I'm losing 2 cycles. But here you have started using tens of cycles, and we have not even considered this. Suppose if this one also had 10% miss rate, then you will have to go here, and your miss rate would be tremendous. So this is the whole idea. And if you understand this, basically that means, you have understood about the cache. So once again, does anyone have any question in this one? Because, this is the foundation. Of course, we are going to put this much more scientifically, but, in a big picture type, you should understand it. So if anyone has any question, please type it out in the chat window and I will answer it. Okay, so we have seen this. Okay, question asked is, what is CPI? CPI is, unlike what you guys call it, the CPI is, I also is equal to cycles per instruction. per instruction. That means how many cycles are taken to finish one instruction. And that is also equal to your throughput. So here, just because this fetch cycle we figured out is on an average would take 1.9 cycles, that means your CPI has become 1.9 instead of, you may say that, this is taking only 1 nanosecond, this is taking 1 nanosecond, this is also taking 1 nanosecond, let's assume, and this is also taking 1 nanosecond. But because this is taking 1.9 nanoseconds, your CPI, cycles per instruction, is becoming 1.9 instead of 1. So as I told you, ideal CPI is 1 in inline pipelining. But because of the problems here, we are changing from CPI of 1 to CPI of 1.9. So unlike your resume or unlike your grade sheet, where higher the CPI, better it is, for computer architecture, lower the CPI, better it is. Of course, both CPIs have different meanings, but this is what it is, that CPI means cycles per instruction. So if a processor, someone has asked a question that, if in a processor, the cycles used by the 5 processes are 1, 1, 2, 3, and 5 respectively, then how long would it take to execute one instruction? Well, what do you think? The slowest. So what he's saying is this is taking, say, 1 cycle, this is taking 1 cycle, this is taking 2 cycles, this is taking 3 cycles, this is taking 5 cycles, just assume. Then what would be your throughput? Your throughput would be after every 5 nanoseconds. So what would be your CPI? Your CPI would be 5. It is taking 5 cycles per instruction. Why? Just because this is the slowest. And that would determine, because, what's the point if this finishes in 1 cycle? This cannot move forward till this is stuck over here, right? This can move into this one only if this one can move here. And this one can move here only if this data or this calculation can move up to here, and so on and so forth. But if this is blocking everything for 5 cycles, then everything is stuck behind it, right? So the slowest stage would determine the overall CPI. So if you say 5 nanoseconds, that means for 1 gigahertz processor, this is taking 5 nanoseconds. That means it is taking 5 cycles. So your CPI would become 5, which is very bad as compared to the best of CPI equal to 1. I hope that clears the topic.
Sir.
Yes.
Sir, I have a doubt. Can you please go to slide 4?
Slide 4, yes.
Sir, here processor first find data in level 1 cache,
Right.
and if not found, only then it will find in level 2, right?
Yes.
So, sir, the caches which are directly connected to processor are only level 1 caches, right?
Yes, exactly.
Okay, sir.
So
Thank you.
I will give you an example. Processor knows only level 1 cache. It doesn't know what is behind it. That is taken care of by memory management unit. So processor says, if I want an instruction, I will visit L1 cache, L1 instruction cache. If I want data, I will visit L1 data cache. So it is like a kid, a little kid, when it is hungry, when he or she is hungry, it would go and open the fridge, and it will find that it is stocked with food. So whatever he or she wants to eat or drink is there. So in a kid's mind, the fridge is the provider. It has got everything. But it doesn't understand that to stock the fridge, his parents would have to go to the supermarket or a grocery store, buy groceries and stock the fridge. What parents don't understand is that, to stock the supermarket or grocery store, someone has to go to the manufacturer or the producer and, get the stuff from there to here. So there are different stages at work. But for a little kid, fridge is the thing that if I want something in the fridge, it is not there, then someone would work hard, get the stuff from somewhere and put it in the fridge, and then I will eat it. Right? So similarly, processor. It says whatever I want, instruction I want, I will go to L1 instruction cache. If I want a data, I will go to L1 data cache. And in a simpler processor construction, you can assume that processor will wait. If it doesn't find it in instruction cache, the required instruction, that will say, okay, I will wait as long as you get it in L1 cache, I will have to wait. So your program will be delayed. And that memory management will do run around and go to the next lower level, which is L2 cache. Or do you have this particular block in you? Okay, I'm going to discuss what a block is. Let's just say if you have this particular memory address with you, if L2 cache denies, then it will go to main memory and then say, okay, do you have this? We are not going to talk about beyond RAM because then it becomes part of operating system course. Does it make sense to you?
Yes, sir. But sir, here why are we don't connect everything to processor? Because then speed will be low.
Not really. See, processor does not want to take responsibility of going through various levels. Processor will say, I don't have much time for that. I will just go to instruction cache. If it is not there, I will wait till someone puts it in the instruction cache. So for that kind of work, you have a separate dedicated unit known as memory management unit. So memory management unit will take responsibility of looking into this L2 cache. And then, if it is there, then, it will take it from here and put it over here. And then if it is not found here, then, this L2 cache will contact main memory and main memory would supply it to L2 cache. So processor does not do that work of figuring out where the data is. It gives that responsibility of main memory management unit. Second question is, why not directly take the data from L2 to processor? I will answer that question, but maybe after 1 or 2 lectures, and then things would become clear. Sometimes we do it and sometimes we don't. When we do it, we require some checks and balances. And I will tell you why, if we do it, why we should do it, and what precautions do we take. And if we are not doing it, then I will give you advantages of not doing it. Okay. So give me some time, and we are going to come to that particular topic, that why processor does not take something directly from L2 rather than going from L2, putting it to L1 and then bringing it to processor. Okay.
Okay, thank you, sir.
Okay, someone has asked a question: do the CPI depend on the processor speed? As then the duration of the cycle will decrease. Okay. So I think these are the things you have to keep in mind. Suppose if I say that this instruction is taking 1 cycle to execute, now 1 cycle can have different time periods. So 1 cycle could be of 0.5 nanoseconds for a 2 gigahertz processor. It could be of 1 nanosecond for 1 gigahertz processor. It could be of 2 nanoseconds for 500 megahertz processor, and so on. But when you keep unit as a cycle, you say that in a RISC processor, 1 instruction should be executed in 1 cycle. If it is a cycle is taking a long time, if the processor is slow, so 100 megahertz processor will take 10 nanoseconds for a cycle, right? So every instruction is executed in a RISC processor in say 1 cycle, but the cycle times may be different. That what is the time of this cycle? For slow processor, it might be 10 nanoseconds. For very fast cycle, it could be 0.33 nanoseconds. So that's the difference between cycle and processor frequency. Processor frequency can go up and down, but 1 cycle is 1 cycle. Does it make sense? So the person has asked the question that do the CPI depend on the processor speed? The answer is no. That cycles per instruction, if it's a faster you make that processor, say, if I have some key that by magic I change from 1 gigahertz processor to make it the same thing as 2 gigahertz processor. That means I'm giving only 0.5 nanoseconds to each stage. And let us say that, I mean, somehow those stages are capable of doing that work in half the time. Then, each instructions would still take one cycle per stage, but, but now the cycle time has been reduced. So CPI does not decrease with increase in speed. Cycle remains a cycle. What reduces, what you're trying to say is total time for execution. So there's a difference between time and cycle. A cycle can have variable times. So what's the need for connection between instruction cache and L2 cache? Because there is the storage of data of 600 instruction, we just need 600 bytes. Well, first of all, if you have got 600 instructions, then each instruction in ARM is 4 bytes. So that is technically a mistake. So 600 instruction would take 2400 bytes. But imagine the programs which you are running, right? Say your Word program, or your Bluetooth program, or any one of your games, your MP4 player. They have got hundreds of thousands of lines of code. You can't fit everything into L1. Right? You can hardly fit everything into RAM because the programs are so large. So that's why, and we will also say that there is also a reason that you will have to suppose L1 cache. I'm just jumping ahead of this thing because someone has asked a question. I'm going to explain it in further detail. Suppose processor has created a new value of a variable. Suppose if it's a counter, right? It has changed the value of the counter, and suppose it wants to save it into data cache. So that data cache value is now updated. But the same block which is in L2 is not updated. Same block which is in main memory is also not updated. And your hard drive where everything is finally going to be stored is not updated either. So then there will be technique. This is known as a cache coherence. That all caches and main memory and everything should finally have the same value for a variable. But when to have it is a different thing. So we are going to talk about it a little later because putting too many concepts in introduction is going to confuse people. So we'll talk about it later. Someone asked a question. Is register block considered cache memory, or are registered and cache different? Registers and caches are different. So registers are registers. So you have got 16 registers, so they are not part of cache. Cache is separate. Then the second question which was asked was, the person has asked the question again. Sir, as the components were the same, for example, if the decode stage was taking one cycle in 1 gigahertz processor, I believe that's what he wanted to say. So in a 100 megahertz processor, should that not take 10 cycles? Sorry, if it is taking, if decode stage was taking one cycle in a 100 megahertz processor, should it not take 10 cycles in a 1 gigahertz processor? No, I think there is a conceptual mistake. So let us refresh our idea. So you have got first is what is a cycle? So cycle, you have this waveform. So this is your rising edge. This is your falling edge. This is again a rising edge. So by definition, this is known as one cycle. Second thing, you talk about frequency. So then the question is, how many of these cycles are fitted into 1 nanosecond? So when you say 1 gigahertz processor, that means if you want to know the time period, so that is right. So your one cycle becomes 1 nanosecond. Now, if you have 100 megahertz, so then your T so that is equal to right. So here your cycle time is 1 nanosecond. So one cycle is 1 nanosecond in 1 gigahertz processor, and in 100 megahertz processor it is 10 nanosecond. But so if you say in my processor I'm running it at 100 megahertz, and it is taking one instruction is taking by definition one cycle, so it is taking 10 nanoseconds to execute it. Now, if I want to bump this processor up and speed from 100 megahertz to 1 gigahertz, first of all, I have to make sure that my work would be finished instead of 10 nanoseconds, it should be finished in 1 nanosecond. So that means either I have to go for a better technology. So instead of using 90 nanometer technology in transistor, I have to go to say 14 nanometer technology. So when smaller the transistor, use faster transistors. And it is not an easy task. And if you have seen the interview with Ayushi Sharma, she is working exactly in this kind of thing. So if your boss asks you that, I know you are running this processor at 100 megahertz, why can't you run it at 1 gigahertz? There are a lot of things which needs to be done. You say, I need to change this, this, and this. Only then I can run it at 1 gigahertz. And why do you have to make changes? You have to make changes because, previously you have got 10 nanoseconds to finish it. Now you have got only 1 nanosecond to finish it. Why? Because one cycle here in 100 megahertz meant 10 nanoseconds, whereas one cycle in 1 gigahertz processor means only 1 nanosecond. Right? So that's why your cycle remains one. You call it this is one cycle. And one cycle by definition is this. From rising edge to rising edge is one cycle, no matter what frequency it is. But how much time period is this will vary according to the frequency. So this time period may be 1 nanosecond for a 1 gigahertz processor, or this could be 10 nanosecond for 100 megahertz processor. So Tarang, is this clear to you?
I had a similar doubt in this.
I think your voice is very slow. I can barely hear it. Can you speak up, please?
Yes, so am I now audible?
Yes.
Yeah. So as you explained in this example of 1 gigahertz and 100 megahertz, so if
Right.
if a same instruction is run on both the processors, so will it run, or we would have to modify the code a little bit?
Okay. See, when you are using as a programmer, you don't care whether the processor is 1 gigahertz or 100 megahertz. You want to execute your program. Only thing is on 100 megahertz processor, your program will take longer to execute because, suppose your instruction is, say there are 100 instructions, right? And let us say each instruction, the throughput is 1 cycle, say CPI of 1, and I'm taking ideal case. Let us not worry about uh, not finding the memory in instruction cache or data cache. Let's say we find everything in there. So that means if I want to finish 100 instructions, program of 100 instruction, it will give me a result in a 1 gigahertz thing in just 100 nanosecond, I'll get the answer. Whereas here, it will take 1,000 nanoseconds, right? So speed would be different in executing on both processors.
Yeah. Okay, so the frequency of the processor just determines how fast it would get executed.
Exactly.
Okay, thank you, sir.
Okay. So any other question?
Sir,
Because I mean, these concepts should be clear. Yes, please go ahead. Someone else wants to ask a question?
sir, in the slide 4, uh, you said for 90% of the time it will first be able to search the instruction in the L1 cache, and for 10% chances it will have to search to be able to find in the L2 cache. So
Right.
for even that 10% chance, first won't it try to search in the L1, and there it will not be able to find, then it will go to L2 cache. So
Okay.
so
You're
it
right.
should take 11 cycles, I think.
Okay. See, the nomenclature, uh, I think we'll come to this, that is how to find AMAT, that is, time for a hit plus time for a, I mean, in a percentage miss into L2. So I think we'll come to that. Right now, let us assume that, if you, because, every uh, thing, which is coming here. So what you are saying is that, here it should be 100, that is 1 into 1 plus 0.1 into 10.
No, sir, I'm telling 0.9 into 1 plus 0.1 into 11.
Okay, I think this page is, let me. So let us talk about just one layer. This is your processor. This is your instruction cache. That is L1 cache. I think refer this to as L1 cache. And this is L2 cache. L2 means level 2. And of course, there is main memory and hard drive on this side, but we are not paying attention to them. And this is unified. Unified means it has got both data and instruction inside it. So technically, based on your point, is that all the requests first come here, and then if it doesn't find here, it goes over here. So technically, if I want to make the previous example correct, it should be just 1 second. Would it not be like this? I'm sorry. It should be point. Don't you think this one is more appropriate?
No, sir, I was thinking that it should be 0.9 into 1 plus 0.1 into 11. So for the, as you said, that 90% of
See,
time,
I think conceptually, probably what I'm trying to say here is, and that, in 100% of the cases for getting an instruction, processor talks to this level 1 cache, right? 90% of the time it finds it over there, and 10% time it has to go over there. So I think let us not discuss this too much right now, because there is a long formula for finding AMAT, and we are going to do a problem in this one. Once we actually discussed different types of caches, we'll go to this problem. But right now, assume that answer should be, it should be something like this, that you first go to L1 cache, you go to L1 cache all the time. So when you consider AMAT, so you will always say time to reach L1, and plus there are other terms. So this is always considered that you always reach over here. So let us not discuss this too much at this point. We'll come back to it.
yes, sir. So I was just asking that first it will try to find in the fastest available memories, then
Yes.
it will.
Yes.
Okay.
So I think conceptually you should also understand how things end up in instruction cache. So let me also put main memory. Assume that this huge block here is main memory. So this huge gray thing is main memory over here. Now, initially your program, this caches are, let's say, empty. You are doing a complete cold start. So then, what it would do is it would start transferring data from you. Say first, when you write a program, where do you save it? You save it on your hard drive, correct? When you execute it, the required blocks would start coming into a RAM. Now, let's say your program is bigger than your RAM size, just suppose. So it would send only the required things into L2. Otherwise, L2 would be all filled up. Or sorry, main memory would be all filled up. Then from main memory, as per need. So initially, all the demands which are made by a processor to instruction cache would all be going to be missed. Because why? It is known as cold start. So initially, you'll get a lot of misses. Then, your cache would start filling up, and then, you will start getting hits. But once again, I'm getting ahead of my self. So at the moment, enough for this particular time, assume that there are 3 levels. There is processor. Right next to processor is L1 cache. L1 cache has separated out into 2 entities, instruction cache and data cache. Then there is L2 cache, which is a unified cache. In some modern processors, you have got also L3 cache. And then, you have got main memory. So any cache other than L1 or any memory structure other than L1, so that means L2, L3, and main memory, they're all unified. So that means both data and instruction can reside in them. And processor will always look at L1 cache to get the instruction or the data. And what is beyond instruction cache or data cache L1, processor doesn't know and doesn't care. That work has to be done by memory management unit. So for now, this is, at least this you should get in your head. Rest of the things will follow. Okay. Now to make cache a success, there is something which is known as principle of locality. This is a very important concept. So there are principle of locality for a given program. There are 2 types of localities. The first one is temporal locality, and second one is a spatial locality. So word temporal means in terms of time. So as the definition which states here, that means current data or instruction that is being fetched may be needed again soon. So we should store that data or instruction in the cache memory so that we can avoid again searching the main memory for the same data. And special locality is that if the item is referenced, then the item whose addresses are close by will tend to be referenced soon. So what it is trying to say? So let us say that you have written a program and it is, let's say, a 10-line program. And this is instruction 1, instruction 2, 3, 4, 5, 6, 7, 8, 9, and 10. And this program has a loop somewhere over here that, if the condition is met, go back to here. So there is a loop which is taking place like this. So here, let us understand what temporal locality means. So in temporal locality, what it's trying to say is, okay, you have used 1 recently, then 2, 3, 4, 5, 6. After 6, there is a loop back. And every program worthwhile has got loops inside. So it says is that there is a temporal locality here that you have used 1. So the chances are that you will be using 1 again. Now, this is a statement is much more correct if it is part of a loop. But there are lots of loops. In fact, most of the time taken in execution of a program is in loops. Why? Because loops, you may say repeat 10 times, repeat 100 times, repeat 1,000 times. So if your program is, say, this big and it has got 1 loop, maximum time of the execution is taken in the loop, right? Going round and round and round. So that's where temporal locality comes into picture, that if you have used 1, chances are that soon you will come back to it. Of course, if it is part of a loop. So that is temporal locality. So then what is spatial locality? In spatial locality, usually you have seen in your program, after 1 you go to 2, after 2 you go to 3, after 3 you go to 4, unless there is a branch. So in 6, your spatial locality is broken, that from 6, instead of going to 7, you are going back to 1. But most of the time, you go step down serially. So spatial locality means that, if you have executed instruction number 2, there are good chances that now you will be executing instruction number 3. So these 2 principles are kept in mind in executing a program or designing a memory architecture. Now, this may tie up with something which was taught to you. It was taught to you that don't use go-to statement, means don't haphazardly jump around in a program. Suppose you have written a program which is so bad, which has got, say, go-to statement after each instruction, that after instruction 1, go to instruction number 17, after instruction number 17, go to instruction number 2023. From 2023, come to instruction number 2. It is possible to write a useless program like this to prove a point. But in that particular program, there is no temporal locality, there is no spatial locality. And if something which is truly random, you cannot imagine, because when you want to say foresee that in my cache, operating system has to see, right, that I need to put this much data into L1 cache, thinking that it will be needed, and I would retain this data again because it might be used again and again. I want to put instruction this and retain it in the instruction cache because the chances are it will be used again and again. Those decisions can be made if there is some pattern in your program. If there is no pattern in your program and it is truly random, that from instruction 1 it is jumping to 2076 and then it is coming to 1011, then you cannot design a cache memory hierarchy system will totally fail. So thankfully, there is a temporal locality and there is a spatial locality. Temporal locality comes because of the loops, and spatial locality usually comes because after instruction number 1, you will go to 2, you will go to 3, unless there is a loop. Other than that, you will keep on going one by one. So because of these two things, we are able to design a hierarchical system which is going to be useful to us. If these two things were not there, then there is no way you can design a hierarchical system which will give you 90% hit rate. If it's a truly random system, then your hit rate would be 0.00 something for a very small 1 KB space, right? So always remember that we are thankful to this principle of temporal locality in your program and spatial locality in your program. We are able to design a cache which would give us good hit rates. Does anyone have any question in this one? Okay, I believe our time stops at 9:45. So I guess we have reached time. So there is still time for someone if someone wants to ask a question. Yes.
Could you repeat what do you mean by what it means by temporal locality?
Okay. So temporal locality means locality within time. And as the definition says, that there is a fairly good chance that if you have used an instruction or a data, in our example, let's talk about instruction, that if you have used a particular instruction, the chances are that soon that instruction will be used again. I'm saying chances are, I'm not saying certainly. And that will come true when you have a loop. Say you have used instruction number 1, instruction number 2, 3, 4, 5. I mean, they have been used recently. And after 6, you're going back into loop back to 1. So that's where your temporal locality principle has been proven correct. I mean, you may say that, when you're using 7, 8, 9, 10, and then, it goes to 11, 12, 13, then, after a while, and there is no loop back, then you will say, okay, then this temporal locality is not working there, but, there is a principle of spatial locality, which is working. So either of those two things would be there. And I mean, if you write a truly bad program, then there is no temporal locality, there is no spatial locality, and it is truly random, so your things will not work well. So temporal locality means time-wise saying that if you have used an instruction at this point of time, chances are that you are going to use it again. But that statement is true only if it's a part of a loop. But there are lots of loops in a program, so there's a possibility that temporal locality would be there. And second thing is spatial locality means your process has to define which one to fetch next. Should I fetch after executing 2? Chances are a whole lot that 3 would be used. So that is spatial locality.
Okay, thank you, sir.
Okay. Anyone else? Okay, so there is no lab this week. You will be getting your marks in email by Friday. And next week, sometime, you will be able to see your answered question papers. Okay, thank you very much.